Okay, let's get started with today's class. Okay, so what did we learn in the previous class? So did you remember? How do you remember? So we learned about abstraction, right? So and then I also explained the abstraction level we will learn in this course, right? So what is the meaning of the abstraction? So you can just think like the abstraction is just simplifying. So in order to simplify something, then we need to hide something which which are uh, which are not necessary, right? So actually so abstraction means that the complex things are just hidden, so hidden under the layer, and then we can just understand them or some interface. Okay, so that's the meaning of abstraction. Also, I explained the different levels of abstraction. So, and then I also mentioned that in this course, I think the internet speed is slow. So in this course, we will learn about the computer system, abstraction level, architecture, and microarchitecture. Okay. So the previous semester, I taught COSE221 in the digital design group. So as you can see, the layer of this the abstraction level. So that is the layer of covered by the design with the logic layer and this the surface layer. It's a lower layer than the computer architecture layer. But in this course, we will cover architecture and microarchitecture of computer system, right? So I just showed some different levels of abstraction, and then so I briefly explain how applications are executed by computer hardware, right? So the computer hardware, like a processor, can only understand machine code. It is because a processor. A processor is so kind of is the system, and I also explained that if the system can only understand digital signals, it's a 0 and 1. So it means that in order to execute, in order to run some application, these applications need to be translated. And then this translation step is called compilation, or in Korean, it's compile, right? Compilation. So it's the noun form of the compile. Okay. So and then I also briefly explain how typical computer systems are organized. Okay. And then I also learned about some semiconductor technology and the processor technology. Okay. Okay. So in this time, so we will learn about performance metric of control system. And then, in the previous class, I showed this analogy. So this analogy shows some different metrics of performance, the performance of aircraft. Okay, and then actually when everyone actually we measure the performance to compare different systems, right? And then so for example, in this analogy, to compare the performance of aircraft, then we can just compare the capacity, the capacity of passengers. Also, we can compare the speed. Okay, and then we can just generate the new performance metric like this. Oh, let's work. Okay, so I don't mind, but my pen does not work. Okay, so I will use my finger. So as you can see, so I need to use my mouse. Okay, so as you can see, we can generate the new metric such as the capacity of a passenger multiplied by speed. So what does that mean? If we just multiply capacity, so that is the number of passengers, and then if this number of passengers is multiplied by speed, it means number of passengers per unit time, right? Right. So we can generate a new matrix like this, like this. Okay. So also in the previous class, I just showed the two different metrics of a computer system. So and then usually we use these two metrics frequently for comparing the performance of a computer system. So what are they? The response time and throughput. So what is the response time? What is the response time?
Time it takes to respond.
Yeah, right. Obviously. Right, that is good. Okay, good. So, response time is the execution time. It's the time gap between the start time and time of a certain application. So that is the response time. And then we use another terminology, latency. Okay, latency. LATENCY, so latency. Actually, you know, so we frequently, okay, now I can use my pen, the latency. So we frequently say, oh, my smartphone is faster than yours, and then faster. So in order to compare the faster or slower, then we need to measure execution time. So actually it's the response time. And then in other words, it is called latency. Okay? Actually the definition is the same. The latency is that it's time gap between the start time and end time. Okay? And then what is the meaning of throughput? So, you know, these are very important terms. These are very important performance metrics in computer system. What is the meaning of throughput? It is related to the amount of work done by a computer system within unit time, such as the megabyte per second. Okay, so this megabyte represents the size of data performed by a computer system, right? So processed by computer system. And then this amount of work is divided by time. That means the throughput. Actually, you know, we use frequently this method like the flows. So actually, we use blocks to compare the performance of GPUs, right? GPUs. So you know, so when the NVIDIA CEO mentioned the performance of their GPUs, and then he frequently uses the terminology blocks. So what is the blocks? It means the floating operations per second. Okay. So as I mentioned, floating operation, then represent the amount of work, and then it is divided by the unit time, the response, the time. So that we can measure the throughput. We frequently use these two performance metrics to compare or measure the performance of computer systems. Okay, so this is the definition. Okay, response time and throughput. Okay, so but you need to understand the meaning of these two performance metrics. So actually, in this course, we will use these two metrics frequently. Okay. Okay, but this time, so this is in this time, so I will focus on the response time to represent the performance of a computer system or the performance of a processor. Okay, so just you need to remember that in this time we will learn about the response time, and then I use response time to compare the performance of different computer systems, right? Okay, let's see. So then what is the performance? Okay, so let me mention the performance of a computer system. So I repeatedly say that you can frequently say, oh, my computer is faster than yours. So faster or slow. So I also mentioned that we can just compare faster or slow the speed of the system by measuring execution time or response time. But you know, slow means that response time is a long response time, right? Slow means that so we just execute a certain program or certain application, then oh, my computer is slow. So it means that the response time is long. So it takes long. Okay. So long response time means that it's slow. And what's the best? So fast. So oh, my computer is fast. So which means that performance is high. It's actually short response time. Okay, RP, the response time. So you can say that oh, performance. So you can say that oh, the performance of my computer is high. So which means that it means my computer exceeds short response time, right? So actually performance is the inverse of response time. Obviously, right? Right? So I think it's easy to understand. So you need to remember that the performance is 1 over execution time. Okay, so also you need to remember that in this class we just focus on response time. Okay, so then how can we compare the performance of two different systems or two different computers? So for example, the computer X, the computer system X is n times faster than Y. Then in order to compare the performance, then we just compare the response time, right? So firstly, we need to measure the response time by two computer systems X and Y, right? Then how can we compare? So this is the equation. So we can say that oh, X is n times faster than Y. So which means the performance of computer X, is n times higher than the performance of computer Y. So performance of X is divided by performance of Y. And then I said that performance is the inverse of execution time. And then I also said that in order to measure the performance, we need to measure the execution time. So it means it is equivalent to the execution time of computer Y is divided by execution time of computer X. Because why? The performance is the inverse of execution time. So actually, this is very important. So and then I guarantee that the one question of the midterm will be asked for the performance comparison, right? And then so actually you need to remember that you need to calculate the execution time to compare the performance. Okay? But the performance is the inverse of execution time. So it means N. Okay. So this is the example, it's a very simple example. So I think everyone can understand this concept easily because in real world we frequently use slower and faster to compare the performance of different systems, right? So and then slower means performance is slow, so which means execution time is longer. Okay, let's see the example. The time taken to run a program, it's the same program, right? So in order to compare the different systems, then we need to set the same environment or same configuration, right? So in order to compare the performance of two different systems fairly, then the same program, okay, run the same program, and then measure the execution time. It takes 10 seconds on computer A, then 15 seconds on computer B. Then how can we compare the performance? It's easy, right? So we need to calculate of A divided by of B. So it means the execution time of B divided by execution time of A, right? By this equation. And then we can use the 15 divided by it's the 1.5. Okay, it's easy, right? So A is 1.5 times faster than B. So this is the equation and then definition of performance comparison. Okay, we always use this metric to compare the performance of two different systems, right? It starts from the definition. Okay, you need to remember the definition. Okay, and that's it. Okay, but we need to consider some different aspects of the computer system. So in the previous class, I explained that a computer system is a very complex system. And then it means a computer system is composed of many different components, right? So we already learned a computer system is composed of CPU and main memory, storage, and I/O devices. Also, in order to run a software, then we require operating systems. And then, actually, we also on the same computer system, many different applications are run actually, right? So if you check the launched processes on Windows, then you can find that many processes are running on the same computer, right? So, which means the response time of one application can be influenced by many factors, right? So as I mentioned, our computer system is composed of many components. So it means that the execution time of one application can be influenced by operating system. And then other applications. Also, the response time or execution time can be influenced by network speed, right? So if the network speed is slow, you can say, oh, my smartphone is slow, right? But Also, it can be also influenced by many other factors like the speed of storage system, and then your typing speed also. Then it is influenced by many factors. So actually, well, I mentioned that in order to measure the, in order to compare the performance fairly, then these configuration need to be the same. But problem is that my application, the response time of my application can be influenced by many other factors. Okay, so if we just consider these factors like the processing, the I/O devices, and then operating system override, and then this response time is called the elapsed time. So elapsed time means the actual response time in passing to users. Okay, so actually these factors need to be considered. Okay, I/O device, operating system, and then many other applications. But for the elapsed time, we cannot. It's very difficult. It's very difficult to compare the performance of different systems using elapsed time because this elapsed time can be influenced by many factors. So it means that it can vary. It can vary time by time. Okay, so usually, in order to compare the performance of two computer systems, actually, in order to compare the performance of two different CPUs, okay, compare the performance of two CPUs, we use CPU time. So what is the CPU time? So these factors are ignored. It's removed. We just execute our program on CPU directly, then we can measure the elapsed time. So response time. So we can measure the execution time of pure execution time of our application only by CPU. Okay, this is the CPU time. So actually, so in this time, so we will focus on the CPU time. Okay, we need to ignore these factors like processing, the I/O device time, the operating system overhead, and then some idle time, and then influenced by other applications. So these factors will be ignored and can just measure the CPU time to compare the performance of two different CPUs. Okay. Okay. Then before explain about the CPU time, also before explaining about the performance of the CPU, and then I believe you need to understand how software, how application is executed by a CPU. Okay, this is your application like app. Okay, and then I also I mentioned that not to execute a certain application, this application needs to be translated into machine code. Oops. Okay. And then, so actually, one line of machine code is mapped to the one instruction. What is the instruction? Such as the add, sum, multiply, and load. So actually, these are examples of instruction. Examples of instructions. What does that mean? One add instruction. So CPU can execute one add instruction, and then after that, CPU can execute another instruction. Okay. So actually, CPUs can multiple instructions one by one. So you need to understand how a processor, how a CPU executes instructions. There are many instructions. If our program is compiled, many instructions will be generated. And CPU just run is many instructions, it's a group of instructions, one by one. So one instruction is executed, and then another instruction is executed, and then the next instruction is executed. So you need to understand the instructions are executed step by step, instruction by instruction. Okay. So you need to understand how instructions are executed. So firstly, you need to understand instructions, and you need to understand about the clock. If we took the logic design course, then I believe you can understand about clock signals. Why clock signal is important? Because you know the CPU is the system, okay, and then this the system is working with clock signals, okay. So let's review what we learned in the logic design course. So this is the typical structure of typical is the system. Okay. So this is the clock signal, and then this is the flip-flop, right? Flip-flop, and then also this is the another flip-flop. Then this is combinational logic. Okay. So this system is composed of many blocks like this. Okay. And then how this system works. Okay. So this is the clock signal, and then at every clock edge, the clock signal looks like this, right? So it's repeated signal, and then this rectangular signal is repeated by within clock period. This is the clock signal. So at the rising edge of the clock, signal is given to the input of combinational logic. So this is the input of combinational logic, and then after some delay, this combinational logic generates the output. Okay, and then this output signal is sampled by next edge. So this is the next edge. That's the rising edge of the clock signal. So this is the basic operation of the system. And then the CPU is a kind of the system. So which means CPU also works like this. Okay? Then why is it important? So I said that CPU execute instructions one by one. So one instruction is executed, and then the next instruction is executed, and then something like that. And then I also explain about the operation of the system. So at the rising edge of clock, a signal is input, and then the signal is delivered to the combinational logic, and then output is generated, and then this output is also sampled by another flip-flop. This is the basic operation of digital system. Then, firstly, CPU execute one instruction, and then the next instruction. So instruction by instruction. And second, CPU uses clock signal. So it means you can just imagine that CPU execute one instruction during one clock period. It's not always true, but we can just understand how CPU execute instruction. So CPU execute one instruction by instruction, and then CPU uses clock signal like this. So it means that at the certain rising edge of the clock, the CPU receives a certain instruction, and then during clock period, this instruction is processed, and then result is generated. Okay, and done. It's done for this instruction. And then in the next clock, CPU receives next instruction. Okay, and then this instruction is processed by CPU and result is generated. And that's it. It's done. Next instruction at the next clock edge. The next instruction is then pulled and then received, delivered to the CPU. So we can understand. So actually in chapter 4, we will learn about the detailed architecture of the CPU, but then you can know that this is not true actually, right? But in this time you can understand CPU works like this. So that's why I explain how the CPU execute an instruction, then how the CPU use clock signals for sampling instructions or input signals. Okay. So this is the simplified abstraction. It's a very simplified operation of CPU, operation by CPU. Okay. So, and why? Why did I explain the operation of CPU like this? So I said, if it is not true, actually in chapter 4, we will learn how CPUs receive instructions or read instructions, how these instructions are executed and processed by CPU, right? But it's a simplified view. It's a very simplified view. So you can understand how CPU execute instructions one by one. And then it means the clock at the rising edge of each clock, CPU can receive one instruction, then this instruction is executed. Okay, it's a very simplified. Okay, then why? Why did I explain the operation of CPU like this? It is because I am explaining the concept of performance using the execution time, which means we will use instruction. Okay, first instruction and clock period. We will use number of instructions and clock period to calculate the execution time for one application. Okay, that's why I explained about the instruction and clock signals. Okay, let's see. Okay, so this is the CPU clock. Then I already explained the. So this is the typical clock signal, and then is rising and then falling edge of the rectangular signal is repeated, and then this signal is repeated. Actually, the period, the repetition period is called the T, and then this T is the time between this rising edge and the next to rising edge. So this is the clock period. So clock period. And then what is the clock frequency? Clock frequency we frequently use letter F. So clock frequency F is the inverse of clock period. Okay. So for example, oh, my CPU, my Intel CPU, the clock frequency is 2 gigahertz. What does that mean? It's a frequency. 2 gigahertz of the clock frequency means that is the number of clock cycles. The number of clock cycles, the frequency. Frequency means actually the number of clock cycles per unit time. So then what does 2 gigahertz mean? Hertz is the actually 1 over second. 1 over second. So 2 gigahertz means that there are 2 giga clock cycles. 2 giga clock cycles per second. So which means 2 giga means the 2 to 10 power 9. Okay, so there are 2 billion clock cycles within 1 second. Okay, this is the meaning of the clock frequency. Okay, and which means that if we know the frequency of a clock signal, then we can just calculate the clock period. So clock period is the time gap between the two consecutive rising edges. Okay. Okay. Then how can you measure this CPU time? So CPU time is the response time of application, but the many factors such as the I/O devices or operating system overhead. So those all factors are ignored. Only to measure the execution time on CPU. That is the CPU time. Then how can we define the CPU time? So I mentioned that the clock cycle time is its clock period T, large T. And then how can you measure CPU time? So you know the CPU is the system. So which means application A starts here, starts at this time, and then do. And then A ends at this time. It's a T start and then I need to use the small t. T start and T end. So what is the CPU time? The CPU time is the TE minus T start. Obviously, right? Then we can represent the CPU time using clock cycle time, the clock period, and then and number of clock cycles. Right? We can count the clock cycles between this TE and time and start time, right? So for example, the clocks, so there are if we count the clock count, then the clock count is 1,000. Okay, there are 1,000 clock cycles between TE and TS. Then how can we calculate the response time? This one. So there are the clock count is 1,000, and then if we know the clock period, the clock period is the repeated signal, so which means that every clock has the same clock period, right? Obviously. So the thousand, the clock count is multiplied by clock cycle time, the clock period, and we can calculate the response time of CPU. It's a CPU time. So it is clock count, clock count multiplied by clock period, the clock cycle time. So obviously, right? Then, so you can say, this is obvious. Then why do we need to learn about this? So it is because usually the execution of an application or execution on CPU is usually represented using clock signals. Okay, and it is because CPU is also CPU is the system. Also, CPU is running with the clock signal. So that's why we represent the CPU time using clock count. Okay, clock count multiplied by clock period represent the CPU time. And then clock. So this is the clock period, and then the clock period is the inverse of the clock frequency. Then it is equivalent to the clock count divided by clock rate. So this is the clock frequency. Right. Then, if an equation is given, then we can think how to improve the performance. So this is the equation. So if the CPU time, okay, CPU time is the clock count multiplied by clock period. Then, we want to improve the performance of the CPU. How? So firstly, we need to increase or reduce the CPU time to improve the performance, increase or decrease about CPU time. CPU time needs to be decreased, right? Obviously, right? So decreased. Then how? To decrease CPU time, CPU time is composed of clock count multiplied by clock period. Then, if we reduce this clock count, or if we reduce clock period, then it can decrease CPU time, which means we can improve the performance of this GPU, right? Understand? And how? So that's why we frequently use clock frequency to compare the two CPU. So for example, the Intel i7 works with the 4 gigahertz clock. Intel i5 works with the 3 gigahertz clock. If we just see this information about the clock frequency, then we just assume that i7 is better. Why? Clock period is shorter than the i5. So means that the frequency is higher, right? The frequency is the inverse of the clock period. So if we see that this equation, then we can say, in order to improve the performance, we need to reduce the clock count, or we need to reduce the clock period. So it means we need to increase the clock frequency. What? And so actually, clock period is influenced by hardware technology, and then clock count. clock count is usually, I said usually, influenced by software. Okay. So for example, so if we use better or improved semiconductor technology, we can use clock theory. It means we can increase clock frequency. And then this, I said this is the software part, the usual software part. So in order to reduce the clock count, we can develop better software. What we can use improved software algorithm. Okay. So if we see this equation, then we can say we can say, oh, not improve the performance, then we can improve the software, or we need to improve the hardware. Okay. Okay, so this is the example. So computer A, you use the 2 gigahertz clock and then 10 seconds of CPU time. And then, so you are requested to design the better computer, the better CPU is a P. And then the goal is to design reduce the CPU time to 6 seconds. Then we can use the fast clock, but it increase the number of clock cycles, so the clock count by 1.2 times of the original clock cycle. Then we can calculate the frequency of the CPU B or computer B. Okay. So this is the clock frequency of the B. So from this equation, CPU time is the clock cycle or clock count divided by clock frequency. So which means the clock rate or clock frequency of B is equivalent to the clock cycle divided by CPU time. Okay. And then the clock cycle is the 1.2 times of the clock cycle, clock count of computer A. So this is, and then the CPU time, the goal of CPU time is 6 seconds. Okay, and then we can easily calculate the clock cycle of A, right? It's the CPU time A multiplied by clock rate or clock frequency. So this is the middle. Then we can calculate the target frequency of the CPU B. This is the example of the performance comparison, performance related questions. Okay. Then we can also use the different terminology or different vectors to calculate the CPU time. Actually, this is very important part. Okay. And then this equation will be frequently used in this course. Okay. Clock cycle. So we already learned that CPU time is equivalent to the clock cycles multiplied by clock period, right? And then let's divide this part. It's a clock cycle part. We can define clock cycles as the instruction count. Instruction count multiplied by required clock cycles per instruction. So what does that mean? So I explained that for CPU, this is the CPU, and then CPU receives instruction, right? I prefer to use IMST for representing instructions. Just CPU. And then also I explained that CPU receive instruction one by one. Okay, this is very important concept. So we want represent the performance using instructions. Okay, so firstly, performance, the execution time. Performance is represented using clock cycles or clock signals actually. Clock signal, we use the clock count multiplied by clock period. Why? Because CPU is a digital system. The digital systems work with clock signals. That's what I explained. And then now we represent clock count using instructions. Understand? It is because CPUs receive instruction, and then each instruction will be executed one by one inside of CPU. That's why we want to represent the performance using instructions. Okay, again, it means that clock cycles. So it means clock count can be represented using instruction count. And then number of cycles, the average number of clock cycles per instruction. So it means the cycles per instruction represent required clock count per instruction. So required by one instruction. So it means one instruction will take multiple cycles also. So it may take more than one cycle, actually. Usually more than one cycle. So we can represent the clock cycles like this. Then what is the CPU time? CPU time was the clock cycle multiplied by clock period, and the clock cycle can be replaced with this equation. So it means instruction count multiplied by cycles per instruction. This is the CPI. It's called the CPI. It's also very important performance metric in CPU, and then clock cycle time. Okay. So I frequently use T. So response T is the instruction count IC multiplied by CPI, the clock per instruction multiplied by clock period. Okay. So just to remember this equation, it's actually very important equation. Okay. So we can represent the CPU time using instruction count and clock period with CPI. We frequently use CPI also for comparing the performance of CPU. Also, we can use the instruction count and then clock period or clock frequency. Okay? So this equation is very important. So just you need to remember that sometimes, so the problem sometimes, so I said that we frequently use CPI to compare the performance of two CPUs, but you must not be confused about the CPI actually. So because in order to calculate the CPU time, then actually we require these all factors: instruction count, CPI, or clock frequency. Okay. Just remember this equation. So then why this equation is important? Because this equation explains how we can improve the performance. So like this. So if we just to represent the CPU time like this, then we can just divide the performance factors like the software part and then hardware part. the software part decides the clock count, and then hardware part decides the clock period. The same. We can rewrite the CPU time like this. Instruction count IC multiplied by CPI multiplied by TC clock period. So, which means in order to increase the performance, then we need to reduce the instruction count, or we need to reduce the CPI, the number of clocks per instruction, or we need to improve the, we need to reduce the clock period. Okay, and then these terms are related to different research field of the computer system or computer engineering. So for example, how can we reduce the instruction count in a program? It's purely software part, right? So, we can write the code using the high-level language like C, and then this code is compiled by compiler. Then the machine code is generated. Okay, so and then this machine code is executed by CPU. So which means the quality of high-level language code, also the quality of compiler, also compiler compiles this high-level language code based on the instruction set architecture, which means ISA. These factors decide the instruction count. So firstly, software. So it is determined by algorithms or the ability of the software engineers, right? And then also compiler is also important. So the quality of compiler also decides the instruction count. So ISA. Instruction set architecture. So in chapter 2, we will learn about the instruction set architecture, and you can understand. You will be able to understand why instruction set architecture decides the instruction count. So these parts, algorithm, ISA, and compiler decides the instruction count. Okay. How about the CPI? CPI is the number of clock cycles taken to execute in a single instruction. It's the average clock cycle. So actually it is determined by hardware. It means actually architecture or microarchitecture of a CPU. Okay, so CPI is influenced by architecture of a process. Okay? And then, as I explained, the frequency is highly influenced by semiconductor technology, also the design, the quality of the system design. Okay, okay, then using these two different terms, then we can just define which factors need to be improved or improving the performance of a computer system. Okay, and then we can also understand that in order to improve a computer system, then software parts and then hardware parts need to be improved. Okay. So using this equation, then we can just represent the different factors of performance of a computer system. Okay, so this is another example, and you can just leave it to this slide for comparing the performance. Okay. Oh, so I briefly explain. So this computer A and computer B, the cycle time is, so cycle time is the clock period, okay? The clock period. then CPI is given, and then same ISA. And then which is faster? How can we calculate? How can we compare? Which is faster means that, oh, we need to calculate. So we need to just start from the definition, right? It means part A divided by part B, and then I explain that this is the execution time of B divided by execution time of A, right? Then how can we calculate? It's by the equation we learned in the previous slide. This is the instruction count multiplied by CPI multiplied by PC, the of B, and then instruction count CPI PC of A. Right. And then actually, oh, we know the TC of A, the clock period of A here, here, right? So this is the clock period. We know this one, or CPI, oh, we know this one. And then clock W, or we know this one, and we know this one. How about IC? Where is IC? Instruction count. In ISA. So actually, in this slide, we need to give another information such as the same program, the same application, the same code, same high-level code, HLM code, and then this code is compiled by same compiler with the same compilation options. Okay, so which means then also the same ISA, the instruction set architecture. So which means IC is the same. So I said that, oh, it's the same program, same application. The same application is compiled using the same compiler with the same compilation option, using, and then for the same instruction set architecture. For example, for the same x86 or for the same ARM ISA. Then IC is the same. Because the IC is the same, or this is, you can remove this part, then you can just compare the performance using CPI and clock period. Okay. 1.2. Understand? Okay, so it's very important. Okay. Sometimes we may make mistake not considering the same item. So this is because in order to calculate the entire CPU time, these all three factors are required. Instruction count, CPI, and PC, clock period. But in this example, I mentioned the same item, so it means that the instruction count is the same. But if we use the different ISA instruction set architecture, then we cannot compare. Okay, you understand? It is because the ISA is related to the instruction count. And then, as I mentioned, we need to start from the definition. Okay, so it's just execution time B and A, then the equation. So then how can we calculate the CPI? So actually, different instructions pick different clock cycles. So for example, the add instruction may take one cycle, and then multiplication may take 32 cycles. So usually multiplication is more complex than add operation. So the multiplication may take more cycles. Then how can we calculate the CPI? Actually, different type of instructions exhibit different CPI. Okay, so which means we need to average all these different CPIs of different instructions, right? So this is the example. So we can actually because different instructions exhibit different CPI, and the total clock cycles are summation of CPI multiplied by instruction count. So for example, this is the program A. So A includes the 32 add instruction and then 1 multiply instruction. Then how can we calculate the total clock cycles? So obviously, it's 32 multiply 1, so cycle 1, and then plus 1 multiplied by 32. So 32 cycles per multiply, so it's also 64. So this is the total clock cycles for application A. So we can calculate the clock cycles like this. So you need to remember that different instructions may exceed the different clock per instruction. So in order to calculate the average CPI, then which means that we need to know the weight of instruction, right? So for example, this is the program A, right? And then the program A includes the 40% of add instruction, and then the CPI of add instruction is 1. And then this program A includes the 60% of multiply instruction. Then CPI of multiply instruction is 32. Then how can you calculate the average CPI for this application A? Obviously, we can multiply the CPI of a certain instruction with the ratio, the weight of instruction. So this is the weight of add instruction is 40%, it's 0.4. It means the average CPI is the 1 multiplied by 0.4, and then the ratio of multiplication is the 60%, then CPI is 32, which is the 32 multiplied by 0.6. So this is the average CPI of application A. You understand? Because there are different fraction of different type of instructions. So we need to calculate this. So we can calculate the CPI like using the weight of the instruction. So that is the fraction of instructions over total instruction. Okay, then because I mentioned that different type of instruction exhibit the different CPI. So you need to also multiply the CPI. The CPI is multiplied by fraction of instruction. Then we can calculate the average CPI. You understand? So it means actually different applications also exhibit different average CPI. Right? Because for example, application A may include the 64 multiply and then 1 add. And then application B has the 1 multiply plus 64 add. Then the CPI is different, right? Because of position of the multiply and adding functions. This is the example. So this is the another example that calculate the CPI. So this is the instruction class, so different instructions A, B, and C, and then CPI for instruction class, so 1 to 2. So this is the instruction count in sequence 1. This is the instruction count in application A, instruction count in application B. So you can find that there are different number of composition or instruction in sequence A and sequence B, sequence 1 and 2. Then how can you calculate the CPI? So CPI is the clock. The definition of clock CPI is the clock cycle divided by instruction count, right? Because it's the clock cycles per instruction, right? Then for the sequence 1, the total instruction count is 5. Then what is the total clock cycles? You can calculate the total clock cycles by multiplying instruction count multiplied by CPI with a certain corresponding instruction, right? So if the total clock cycles is 10, so average CPI is 2. Sequence 2, instruction count is 4 plus 1 plus 1 equals 6. The total clock cycle is 4 multiplied 1, 1 multiplied 2, 1 plus 3, 9. So 9 divided by 6 is 1.5. So this example shows that different applications have different fractions of instructions. So actually the CPI is also influenced by applications, right? This is the this example shows that. Okay. So this is a summary. So you need to remember this equation. I said this equation is very important. The execution time is instruction count multiplied by CPI multiplied by clock period. Then as I explained, different parts of software and hardware influence different terms of the CPU time. Okay, so I will stop here. Any questions? So again, I said it's one of the same if you use the book high time. So they don't have something compared by the kind of the different kind of I was never sometimes these things. Thank you for listening and see you.